All right, so welcome to this talk about the virtual machine design for parallel dynamic programming languages. I'm Remigius Meyer from ETH Zurich, and I did this work together with Armin Rigo from the PyPy project and Thomas Gross, my advisor at ETH in Zurich. Right. So let's first talk about dynamic languages. I guess all of you know some of the examples on the right. There's JavaScript, Ruby, Python, and so on. And we usually associate a few properties with them. So for example, we might think of them as high-level languages, as dynamic, of course, but also often as inefficient. Well, this started to change recently. Like in recent years, with the development of just-in-time compilers, this is not true anymore for all languages. So the JIT, the just-in-time compiler, has become a critical component of high-performance virtual machines. Good examples for that are, of course, the JavaScript in the browser. Nowadays, every browser has a high-performance virtual machine with a just-in-time compiler. There's LuaJIT for Lua and PyPy for Python. And indeed, if I run a small program on a Python interpreter, so a virtual machine with just an interpreter, it might take something like 40 seconds. If I then run it on a virtual machine with a just-in-time compiler, I can get this down to 10 seconds. So I get a 4 times speed up for free, sometimes even more. But at this point, an application developer is not done nowadays. They have to consider modern hardware, which is usually parallel. So a Python developer might start using threads here. So here I try to use 8 threads, distribute the workload, and hope that I get a speed up, but instead I get a slowdown. So clearly, parallel execution was not successful. And this affects some popular languages like Python and Ruby, as we also heard in the talk before. And we want to highlight one issue here, which is about the just-in-time compiler and concurrency. So this is from the perspective of the virtual machine designer. So what does a JIT do? It might look at a function like this. It's called foo. It has an argument x, and then it assigns the value of 5 to one field of x. It then uses that field and multiplies it with another field and returns the result. So a smart compiler, or actually any compiler, might see, okay, we just assigned 5 to this field, and probably at the point where we do the multiplication, x.a is still 5. So it didn't change. And it will do a program transformation called constant propagation, and instead of reading the field from memory, we will multiply by a constant instead, which is faster. But what we can see here, that these optimizations require assumptions to be made. So the JIT compiler assumed that at the point of the multiplication, the value is still the same and didn't change, which might not be true if we concurrently run another function that reassigns a with a different value. So that's where concurrency comes in. And there are various ways in which languages can deal with this issue. For example, they can restrict concurrency for the programmer. So choosing, for example, the actors model, there you only can send messages between concurrent computations, no shared memory accesses, so less interference. Or you can choose a suitable memory model with weaker consistency, less guarantees for the programmer, but it's better for the implementer. So this still allows a JIT to do optimizations under concurrency. A good example, of course, is Java's memory model. Well, what happens if a language does neither of that? We saw what happens before. And this applies to Ruby and Python. So they do not restrict the concurrency at all. They have a shared memory model with multi-threading, and each thread can access each other's memory and interfere with it in any way that they want. Also, Ruby and Python have a very strong memory model, which I will talk about now. So the memory model has sequential consistency. I cannot go too much into detail, but basically this means that such transformation might not be valid anymore. So because we made an assumption that a value that we just wrote to memory, reading from the same memory location will yield the same value, that might not be true under sequential consistency. So assumptions like that might not be valid, and of course, as a virtual machine designer, we have to think about how we can regain the ability to make such assumptions. Otherwise, the JIT is just not effective because it cannot optimize. And then, in particular, in Python, we have atomic operations. So for example, you can atomically extend one list with the elements of another list. It's guaranteed to happen atomically. Also, you can atomically sort a list, which might be useful. So as a virtual machine designer, again, we have to ask ourselves, how can we implement such atomic operations over large data structures, which might not be that easy. Of course, there's related work in this area. I will try to categorize it based on two things. For one, do they implement the complete semantics of Python and Ruby, so sequential consistency and atomic operations? And also, do they consider the case of the just-in-time compiler and its optimizations, or basically, do they do it in the context of a high-performance virtual machine? So one approach is the thread-safe object model introduced 2 years ago here, same conference. And also the previous talk was basically an extension of this model. So there I would say they do not implement the complete semantics. Of course, they're trying to get there, so they get an orange cross, not a red one, which is important. So it's kind of a bottom-up approach. They start at Java memory models, and they try to add the consistency guarantees back without losing performance. So indeed, they do this in the context of a high-performance virtual machine, which is Truffle in this case. So there's also approaches that use hardware transactional memory, and transactional memory maps perfectly to the semantics, so we get the semantics for free, but none of these approaches here were considering this in the context of a high-performance virtual machine. Some also use inexisting hardware or just incomplete VMs. And finally, there's our approach, also first presented in 2016, 2 years ago at DLS. We started with the complete semantics, so kind of top-down, and we try to get the performance back. And of course, we do consider the JIT here, right? So what does our approach look like on a high level? So we have this shared memory here, the black box. We have two threads running in there, so the arrows are the threads, and they each run one function. One runs foo, the other one runs bar concurrently, right? The first step that we want to do is we want to separate these concurrent computations from each other. And we do that through duplication of resources and call that parallel worlds. So in a more abstract form, we have these concurrent computations in this shared memory that are kind of entangled and can access each other's memory. And the first step is simply to duplicate the shared memory, create two worlds which are identical, and then have the computations, one computation per world. Right. Of course, we also isolate these worlds from each other, which means that we don't have any interference. So if you run in one world, you will not see intermediate changes coming in from another world. This is important for the just-in-time compiler that needs to make assumptions which need to stay valid for a bit. Otherwise, it cannot optimize. Of course, at some point, the worlds will diverge. So, for example, here we have an object A in the world. First, we duplicate the worlds. We have two worlds with each the same object. So A is the same in both worlds. And then at some point, maybe world 2 will modify the object. So it's become red here. Of course, this means that now it's kind of an inconsistent program state. So the worlds do not agree on what is the program state anymore. And there we do something which we call world reconciliation. On the most basic level, this means we import the changes of worlds into our worlds so that they agree again, so that they, reach a consistent state. We do this continuously and, of course, transparently again. So with that, we reach transparent isolation, meaning that the JIT does not see any interference from other concurrent computations, from other threads, and there is also never inconsistent state. So we don't have out of thin air values or anything like that. That's what world reconciliation is doing. So with that, basically, JIT is completely relieved of any handling of concurrent changes. Right. We also do transactional execution. So basically, any computation that happens in a world will appear to happen atomically, as seen from other worlds. This, of course, helps us with implementing these atomic operations over large data structures, so list extends or list sort in Python. We can just if they run in two different threads, we can just assign each thread to its own world, and world reconciliation will then guarantee a consistent result, meaning that the computation will have happened atomically, both of them. Of course, this is only, parallelization in general is only useful if it gives performance boost, so if the runtime is shorter in the end. So how can we make this efficient? I talked about duplication of resources, which usually sounds bad. So actually we kind of duplicate the whole virtual machine. So each thread or each world is a complete mirror of the virtual machine. And each thread gets one of these virtual machines. Well, we try to make this efficient by doing in-process memory sharing through leveraging hardware capabilities. And this looks something like that. We have the virtual address space of the process, and we place our worlds in this virtual address space somewhere. Now, through continuous reconciliation, we try to minimize the differences between the worlds such that they are largely identical. And of course, the identical parts we then try to share between the worlds. So, and we do that through virtual memory of the x86 CPU in that case. This looks something like that. So we have our physical address space, which is the actual resource that we want to, that we care about. So we have limited physical address space here. And we can change the mapping from the virtual address space to the physical address space. And if an object, here the blue object in world 1 and world 2 is the same, we want to use only once the physical memory for this object. Of course, if the object is different in two worlds, we need to have different memory. So there's one condition for this to work. Of course, the memory must be identical for sharing, which sounds pretty obvious, but it has a consequence. So if you look at this example here, we have two worlds and the same object in both worlds. It's identical, so we want to be able to share the memory. But then let's assume that it has a reference to an object A. But A is not identical in both worlds. So there is one version A1 and there is another version A2 in world 2, right? So now for sharing object B, of course, the memory, the underlying memory of B must be identical, which means that the reference to A1 and A2 must also be identical because the references are stored in this object B, of course. So they cannot be different. On the other hand, A1 and A2 are definitely different versions of A. So they need to be in different memory locations. So we cannot use the memory address, the memory location as a reference. In a sense, on a higher level, we can look at it like this. We have an object B with two, which is the same in two worlds. So it only exists once, in a sense. But there are two versions of A, so there's A1 and A2. A1 in world 1, A2 in world 2. We could, of course, just say we create two versions of B, one with the reference to A1. So B1 references A1 and B2 references A2. But of course, that's not good because this will transitively unshare the whole heap if we do something like that. So this is a bad idea. We don't want to do that. Well, instead, what we need to achieve here is that the same reference resolves differently in different worlds. And of course, this should happen transparently again. Just-in-time compiler shouldn't have to deal with it. And it might happen on each memory access. So it has to be really fast. And our answer to that is that we look at worlds as memory segments, which means that the same object is always at the same offset in all worlds. So here, we have the same setting again. We have world 1 and world 2, and the blue object B is at the same offset in both worlds. That also is true for all versions of an object. So there's only one version per world, and A1 is in world 1 at the same offset as A2 is in world 2. Then we can use the object offset in order to reference to the logical object A. So basically, referencing the logical object means it's the same reference to reference A1 and A2. So we can use this offset as a reference in B. If you want to get to the object version, however, we also have to know in which world we are, and we have to use the world address. So the start address, where is the world in the virtual memory? So world 1 is at W1 here. And if you want to get to the version of A1, we need to add the address of the world address, world 1, W1, and the offset of the logical object A together. So as you can see, this is basically one addition per memory access, which still might sound a bit expensive, but the good thing is we designed it in a way that the hardware can do it for us. So x86 memory segmentation basically does that for free as part of the standard address translation process. So we measured no real overhead in this implementation. So it's really fast. So in summary, we have isolated memory sharing worlds. And these worlds can be really large. So they are entire virtual machines. Because essentially, these worlds are virtual because they only exist in the virtual address space. And we managed to hardware accelerate all of that in commodity CPUs. So any 64-bit CPU can accelerate this. And well, nowadays, every laptop has some kind of CPU like that. Then it's also completely transparent to the chit. So assumptions stay valid. They cannot be invalidated from concurrent computations. And this, again, enables to do optimizations as any chit would want to do. We also talk more in the paper about the algorithmic parts, the dynamic parts. So we do an on-demand page sharing and unsharing, also through the memory protection feature of the x86 CPU. And we also talk more about the transactional memory algorithm, which is important for world reconciliation. Right, so for the evaluation, we evaluate a Python VM. In our case, this is PyPy as a baseline. So PyPy is a Python VM with a just-in-time compiler. It's considered high performance, of course. And our approach is called PyPy STM, which is PyPy with the chit and our backend parallel worlds. We measure the runtime of a few benchmarks here. They are small, but explicitly threaded benchmarks. So explicitly threaded in a way that any Python programmer would use threads. So we compare PyPy STM versus PyPy, and we allow 8 threads to run. That means that a theoretical program could get at most an 8 times speed up if it can perfectly scale with the number of threads. So here's the speed up graph. On the y-axis, we have the speed up. And if it's above 1, it means that the runtime on PyPy STM was lower than on PyPy, which means it's better for us. So we have on the x-axis our programs, and here's one of them, where we get a 6 times speed up. This is actually the example from the first slide that we had. So instead of getting a 40% slowdown, we now get the 10 seconds with the just-in-time compiler down to 1.6 seconds on PyPy STM. So this is the 6 times speed up here. And we have more results. One is larger, the other ones are a bit less significant. But we can see that now with for all of these benchmarks here, we managed to achieve a speed up on modern hardware through parallelization and running on our virtual machine with our approach. So to conclude, we saw that Python and Ruby make the life hard for the chit and for the virtual machine designer in general. That's because of unrestricted concurrency, so multi-threading and shared memory, freely accessible, and a strong memory model because of sequential consistency and atomic operations. But of course, these languages are immensely popular, so we have to find some solution for them. And our approach here is to use parallel worlds, which is the top-down approach, where we start with the complete semantics first and try to get performance back. And it's a transparent approach, which means that it makes the life easy for the chit compiler and actually for the entire virtual machine, which means that also the interpreter, for example, which is in the virtual machine, doesn't have to know about the concurrent computation going on in a parallel world. And also, we get performance back through designing very closely to hardware. So we use some features like the 48-bit address space of 64-bit CPUs, memory segmentation, virtual memory, and memory protection features. And last but not least, it's a real and complete implementation of a parallel Python VM, which is available as an artifact. And with that, I'm done, and I'm happy to take questions.
questions?
Hi, very nice talk.
Hi.
You just showed results on small benchmarks. Can you say something about how it performs for larger applications?
Not really. So the problem is, of course, that, well, since threads are kind of useless in Python for performance reasons, there are no existing programs that just use threads for performance reasons, right? So yeah, we would have to write them ourselves, and so far we only managed to write small programs, indeed.
I guess along those lines, perhaps this is naive, but why the selection of 8 threads, particularly not toggling that value?
So the question was why it's only 8 threads, right? Basically. Yeah. So we think that dynamic languages are usually running on normal hardware, like in a desktop or a laptop. Maybe 8 threads is not up to date anymore. Nowadays you have maybe 16 threads, but overall, I think this is basically the execution environment that we want to focus on for these languages.
In the evaluation slides, which is disappear, but it's okay.
Sorry.
Could you have a baseline? Like, could you measure against the unsafe Pi-Fi, for instance, or this is just too difficult? Like to get an idea of how much the benchmark would scale, basically, without the synchronization.
So without synchronization is pretty hard to do because basically the whole infrastructure that we have there is dependent on there being some synchronization available. So if you just removed all of that, it would just crash.
So the JIT wouldn't, yeah, it wouldn't. Okay.
Yes, it's difficult.
Okay, let's take one last question here.
Hi. So on world reconciliation, the example that you gave, if those two lists were to be reconciled, what would be the result? A sorted list that has the results of the other list? Or do you append first and sort later? Or anything is possible because you forgot to add synchronization, so you get the freedom to decide whatever the result is?
So according to the semantics of Python, both results, both orderings are fine, but what we don't want to have is crashes, of course, and like an inconsistent result where atomicity is not guaranteed. Yes.
All right, let's thank the speaker one more time.